Alright guys, welcome back to streaming. It has been ages since I've last streamed, and yeah, I'm returning with virtual circuit board. However, one more thing, I will not be able to see live chat. I will only sometimes check on it, but don't worry. So I want to tell you about some things while I was away. And so first off, about my CPUs. Yeah, don't bother. So the first CPU which I ever finished, was this one, and it's terrible. So I absolutely do not recommend using it. And what is the VMan settings on this one? It's 15 bits. That is absolutely terrible. So yeah, it's not good, and it's very slow. And you can see that this all this does is it just prints welcome with an exclamation mark. It's terrible. So then the second CPU I've ever done was this, and you can see it uses macros. It also uses bookmarks. Very good. And you can see it's built differently. It has 16 registers, which I absolutely like. It has a very good stack. It has a little ALU here, and it has an absolute mess for decoding instructions, but in return it is actually fast. So currently it has a Fibonacci sequence programmed into it, and yeah, but you can see that even the jump conditions are still absolutely horrifying. So then the first CPU, which is the latest I've made, is x86-8, and that is him. This is my latest CPU, which, as you can tell, it was already programmed to do a multiplication. And so, yeah, but it's still 8-bit, and the reason I don't like it is because, I mean, think about it. You have, so let's just go back to my test world, and so you have 8 bits, right? So I'm just gonna draw that real quick. You have 8 bits, and essentially that means 256 whole addresses we have. And I'm sorry for drawing so slow. Actually, it's 255 because address 0 does nothing. So here you have 255 addresses, which means in total your whole code can consist of 255 instructions, which is terrible. So in the test world you don't have many things. I have a serial adder, this weird register thing that I will never use because it's very space inefficient, and this thing which is basically 2 write 4 read registers, which what it means is that it has 2 write inputs and 4 read outputs in total, which you can control. And also I made this touchscreen, which I am really proud of. However, I haven't made use of it yet, but it works very nice, and that is where 8086 comes in place, because I'm actually working on a 16-bit CPU, and you can see that it has the touchscreen, and I absolutely love this. It has a call stack separately. It has this big stack part, which is just regular stack. Here are the registers, which is 16 of them, but I only use 15 as general purpose, and there is a stack pointer, which will be used to read any layer of the stack, of course. And yeah, this is the ALU in the middle. The flags are determined based on the ALU's output, because I will be using subtracting. And yeah, and here is the outputs of all those. Here's the program counter, the decoder, the other decoders, and currently I'm kind of stuck because of how to wire all this up, but trust the process. And now another project I've been working on is Funny, which basically what it will be is a very fast CPU, a very fast one that hopefully breaks records, because what I'm planning on doing is having a CPU that literally has this, simply just this as the clock, which is 2 ticks per instruction. Now the solution to this is to obviously make it staged, so give stages to the CPU, and currently the stages I have, hold on, I'm just gonna quickly draw them up and explain them in a bit. So FDREW, what this means is F is fetch, which, well, basically it kind of does what it does. It goes to here and fetches the instruction, which is basically updating the program counter. Decode is, well, decoding the instruction. Read, this is actually readout, or actually this is just short for prepare readout, since reading consists of allowing like one specific register to read, which then has to be inputted into the ALU. Then execute is, well, it's actually reading and execution of the instruction at the same time. And it also prepares write back, which means it prepares to write to the specific register which we need to write to here. And then write back is just writing the output of our instruction. And you can see here is our instruction set. We have no operation, obviously, which is needed because of jumps, and because we have to somehow clear all these stages of the previous instructions. Then we have exit, which is obvious. Load loads a register with an immediate value. Copy copies the value of one register and puts it in another. Add sub, it's very obvious, and or XOR not also obvious. But you can see that they have a weird operand combination. That's because, for example, in add, you use both as reading, but you also write back into the first one, just like how real assembly does. And compare sub, which is basically, it subtracts but doesn't write back the value anywhere. Instead it sets flags. And then jump if will jump to a specific memory address if the flags needed are active. Now obviously I'll give a condition to jump if also, which all it does is just unconditionally jumps. And then here are 0, neg, and over. This means if these are for compare sub, if the output is 0, so the two numbers are equal. If the output is negative, so that means that A was less than B, and then over means A was over B in value. Registers are R1 to R4, and currently there is no code. So this is also another project I'm working on, but I'm kind of stuck for a while. So yeah, it's a bit confusing, but I'm working on it. And today I'm thinking of just, also there's this x8642. This was originally going to be a 32-bit CPU project, though you can see that I haven't really made any progress yet. I mean, not like that. I have 16 32-bit registers. I have a whole call stack. I have a whole regular stack. I have the decoder already attached. I have some logic already done. And yeah, here's the ALU, you can see, and you can see it's done very weirdly, like with 2 buses. That's because one bus can only handle 16 different colors or 16 different traces of the regular wires. Obviously it depends on which case you use, but we don't talk about that. And so here's the instruction set. It's very basic, and you can see that most operations actually have a free operand solution, unlike x86-8. That is because there is this thing. So this is the important part. Immediate means that, for example, in moving, you move an immediate value to a register, or you add an immediate value to a register's value. And operation so operand, this means actually all it does is that it specifies that the instruction will not need a second cycle, because that's how these instructions work, but instead it can do it in one cycle. So for example, moving with an operand, that means that you move another register's value into a register. And none is just specified because, for example, if you do immediate, you don't really have a target, like you don't really have the register to read the value out from. However, I'm kind of thinking that this doesn't really work well, and I'm thinking of splitting these two. And about that, how about we try to like make like a base for this 32-bit computer that actually has a much better instruction set, because by now you can see that I designed lots of logic and I don't really want to redo all the logic again, because I would absolutely die if I did that. And with that said, I will be back in a short while. Now I don't know how to do this, so hold on, I have an idea. So I will be back in a while and continue this stream in a way that I'm gonna stop this stream and then I'm gonna start a new one. So be right back, guys. I will be back soon and we'll start the new project. Alright, see ya.